The drift velocity of electrons in a wire of cross-sectional area 1 millimeter squared is given by V0 sine omega t. Now when it carries 50 Hz AC of RMS value 5 amps, that is going to be the value. So the number of electrons in the wire is 10 to the power of 29. Now we need to calculate what is going to be the RMS drift speed of the electrons, the maximum drift speed, as well as the amplitude of oscillation of the electrons. So first of all, we were given the drift velocity. I'm going to write that as a v. Now they said that drift velocity is represented as this, V0 sine omega t. Now we have the frequency f, that is equal to 50 Hz. And we were also given the cross-sectional area. I'm just going to represent that as an A. And that is equal to 1 millimeter squared. Now, if we got this, we could change this to the SI unit for area. Now, we know that 1 millimeter, that is always equal to 10 to the negative 3 meters. Now, if we want to change this to millimeter squared, we need to square both sides. So this is going to be 1 millimeter all squared, and on this side we're going to have a 10 to the negative 3 meter, and that will be squared. Now on this side we're going to have a 1. 1 squared is a 1, and then this is going to be millimeter squared. On the right hand side we should have 10 to the negative 6, and this is going to be meter squared. So 1 millimeter squared is the same thing as 10 to the negative 6. So this is going to be 10 to the negative 6 meter squared. Next up, we need to find out what is the current. Now here we can see that we were given this value, 5 amps, as the RMS value of the current. Remember, AC means alternating current. So we got alternating current of RMS value 5 amps. Now how can we write that? The alternating current is going to be written as a IRMS, and so that will be equal to 5 amps. Now we also got the number of electrons there, which is 10 to the power of 29. What is the charge of an electron? That is represented as 1.602 multiplied by 10 to the negative 19 coulombs. So now we need to find out what is going to be the root mean squared drift velocity of the electrons. Now from this representation, V is equal to V0 sine omega t, we could well say that VRMS, that is the root mean square velocity. That is supposed to be equal to V0 divided by the square root of root 2. Well, the square root of 2 rather. Now, because we got this as well as IRMS, that is going to be that there must be a relationship between current and the velocity. This is called the drift current. This is the drift velocity. Now, what is that formula that relates between the drift current as well as the drift velocity? What is it going to be? Now, we know that the current that runs within a conductor that has some amount of electrons going within it with the cross-sectional area, that is represented as N multiplied by A multiplied by the charge of the electron multiplied by V. You need to hold this formula at the back. It's going to be very useful. So from here, we're going to apply this in terms of root mean square situations. Because of that, we should have a IRMS, and that will be equal to NAE multiplied by VRMS. So from here, we could well find out what is going to be VRMS. That is trying to make this as a subject. So from here, VRMS, that should be equal to IRMS. And that will be divided by NAE. So VRMS here is going to be IRMS, which is given as a 5 amps. That will be divided by N, which is 10 to the power of a 29. And this is multiplied by A. Now A in this case is 10 to the negative 6. E stands for the charge of an electron. Well, I do not really got a space here, but we know this is going to be the value. So I'm basically going to plug that into the calc, find out what that is going to give. So that is going to give us 3.12 multiplied by 10 to the negative 4. So that is 3.12 multiplied by 10 to the negative 4 meter per second. Now we need to find out what is going to be the peak or the maximum drift velocity. That obviously is going to be found using that formula. So let us take these ones out. So from here, we can find out V naught should be equal to V RMS multiplied by root 2. So this is going to be this stuff multiplied by root 2. So we're just going to have that as multiplied by root 2. That gives us 4.41 multiplied by 10 to the power of a negative 4. So this is going to be V naught. Next up, we need to find the amplitude of oscillation for the electrons. Now, how can we find that? Now, you need to know that V naught, that is equal to the amplitude multiplied by omega. This is velocity. Amplitude, that stands for the maximum displacement. So you know that amplitude must be displacement. This is the angular speed. Now we know that angular speed, that is equal to 2 pi divided by the period, or 2 pi multiplied by the frequency. So we got this. Now if we plug this back into this, we're going to have a V naught equal to A multiplied by 2 pi divided by T. This stands for time. So as you can see, we have a scaled form of displacement divided by time. That is basically just multiplied by 2 pi, which is basically the same thing as what you already got as velocity. Velocity is always going to be equal to displacement divided by time. This is almost the same thing. But in the case of alternating current, you're going to have this. Now, in this case, we do not really have what the period is, but we do have what the frequency is. So I'm just going to change this. We know that A was multiplied by angular velocity, which is the same thing as 2 pi f. So I'm just going to have that multiplied with it. This is what we're going to have. So V naught, that is going to be A multiplied by this. Now we need to find the amplitude, so I basically need to take these out. So A, that will be equal to V naught divided by 2 pi f. Now V naught, that was found to be 4.41 multiplied by 10 to the negative 4. Feel free to rewind the video and try to see where that was written. Now this stuff is 2 pi multiplied by f, which is a 50 hertz. So that will be multiplied by 50. The answer here is 1.4. So I think I'm just going to take these ones out. So the amplitude, that is 1.4 multiplied by 10 to the negative 6 meters. Now 10 to the negative 6 is the same thing as a micro. So I could well rewrite this as 1.4 micrometer. Now here is another question for us. An AC source of RMS PD 300 volts and an angular frequency of 200 Hz is applied to a capacitor of capacitance 16 microfarads. Now we need to calculate the capacitive reactance, the RMS current, the instantaneous power, as well as the maximum energy stored in the electric field of the capacitor. Now first you need to understand that this circuit is an AC circuit that contains only the capacitor as the load connected to it. Now if you got such, you need to understand that the power generated or dissipated here is approximately going to be equal to 0. Now why is that? As the cycle moves, as the cycle begins, there is going to be some power which will be generated in this first half a cycle. Now, as the cycle completes, the amount of power which was generated from the first part of the cycle will be returned in the second part of the cycle. And so because of that, that is always going to be equal to 0. Now the same case is going to be for a AC circuit which contains just an inductor connected to it. So this is a circuit which has a pure inductor. This is a capacitor. This is an inductor. So for this, the power is also going to be equal to 0. Because the same thing actually happens. The power which was generated in the first cycle, or in the first half of the cycle, would be ultimately returned in the second part. So because of that, the power would always be equal to 0. So therefore, from this, we have that the power would always be equal to 0. So here, P is equal to 0. Now let us go on to find out what is going to be the capacitive reactance. Now capacitive reactance, that is written as X sub C, that is 1 divided by omega C. Now what is omega? That is equal to 2 pi f. Now f stands for the frequency. In this case, the frequency was given to us as a 200 Hz. So omega should be equal to 2 pi multiplied by 200. That will be equal to 400 Hz. Well, that should be 400 pi. Now you could also write this as rads per second or hertz, basically. So we need to plug 400 pi into this equation. And we also know that the capacitance which was given to us, that is equal to 16 microfarads. Now we need to change this to a full form. So this should be 16 multiplied by 10 to the negative 6. Because a micro is multiplied by 10 to the negative 6. So X sub C, that will be equal to 1 divided by 400 pi. That will be multiplied by 16 multiplied by 10 to the negative 6. So that gives us 49.74 ohms. So this is the answer for the capacitive reactance. We just need to place it somewhere. So you need to hold that at the back because we're really going to use it in the second question. So the second question, we need to find out what is going to be the RMS current. Now RMS current, that is written as IRMS. We already know that the voltage which was delivered would always be. Now this voltage is supposed to be an RMS voltage, and that will be equal to the RMS current multiplied by the resistance. Now in this case it's only the capacitor which is inside, so the reactance as a result of the capacitor, that will be the resistance that will be used. So we need to find IRMS, so we're going to make that basically as a subject. So IRMS is going to be equal to VRMS divided by XC. Now this stuff is given to us as a 300 volts, so that is 300. We found XC to be 49.74. So that gives us 6.04. So that will be 6.04 amps. This is the RMS current. Now we need to find the maximum energy which will be stored in the electric field of the capacitor. Now the energy, I'm just going to call it as E. You might want to write it as a W, whichever you want to write. Those are going to be basically the same thing. Some people may want to write it as a U. And that is going to be equal to 1 over 2 CV squared. This is the formula for the energy or the work done by a capacitor. The energy stored within a capacitor, this is going to be the formula to find it. In this case, we're not just required to find out what is the energy, but the maximum energy. Now, maximum energy in AC circuits, or the word maximum, could also be used synonymously with the word peak. So in this case, we're going to have this as a peak voltage. But we do not really have the peak voltage. How can we find it? We know that VRMS, that is the same thing as V0 divided by root 2. So we could find this as we multiply this with this. So what is VRMS? We have already been given that as a 300. So this is going to be 300 is equal to V0 divided by root 2. So V0, that will be 300 multiplied by root 2. So that is 424.26 volts. Now that we have found this, we're basically gonna plug this into the formula. So the maximum energy, that will be equal to 1 over 2 multiplied by C, which is the capacitance. Now the capacitance was given to us as a 16 microfarads, so that is 16 multiplied by 10 to the negative 6. This will be multiplied by V0 squared. Now we got V0 as a 424.26. So this ought to be squared. So that gives us 1.44. So that is going to be 1.44 joules. This will be the answer. A resistance 70 ohms, a capacitance 50 microfarad, and inductance 0.2 henries are connected in series to a 200 volt supply of angular frequency 400 hertz. So we need to determine all these parameters which are required of us. So first we need to bring out the given parameters. We got the resistance R, that is equal to 70 ohms. Next up we got the capacitance, that is equal to 50 microfarads. We got the inductance, which is equal to 0.2 henries. We also got the voltage, so that is going to be voltage. I'm going to write that as the RMS voltage. And that is equal to 200 volts. And then we also got the frequency. So the frequency in this case, that is 400 hertz. So we need to determine the capacitive reactance as the first question. Now capacitive reactance is represented as a X sub C. And that is equal to 1 divided by omega C. Now omega, that is the angular velocity, and that is written as 2 pi f. Now we do not know what this is exactly, but at least we were given what the frequency is, and so we could well use that to find out what is going to be the angular speed. So this is 1 divided by 2 pi f, and that will be multiplied by c. So this is 1. Now we got 2 pi. And the frequency here is given as 400. The capacitance is given as 50 microfarads. So that is going to be a 50 multiplied by 10 to the negative 6. If you got a 50 microfarads, that could also be represented as a 10 to the power of a negative 6. So that is a 1 divided by 2 pi. And that will be multiplied by 400 multiplied by 50 multiplied by 10 to the negative 6. That gives us 7.96. So this is in ohms. So I'm going to place this here. The capacitive reactance is given as a 7.96 ohms. Now you need to know that capacitive reactance, this is the opposition to the flow of current, which is offered by a capacitor, which is connected in an AC circuit. So you just need to bear that at the back of your mind necessarily. Next up, we need to find out what is the inductive reactance. Now that is represented as a X sub L. Inductive reactance, this is the opposition to the flow of current, which is basically offered by an inductor which is connected to an AC circuit. Now mathematically, that is represented as a 2 pi f multiplied by L. Now we already know that 2 pi f is the same thing as omega, so this could also be represented as omega L. So we know that f, that was given as a 400. And we got to place an L there. Now L here is given as a 0.2. So let us find what that is going to give. So that gives us 502.65. So this is XL. I'm going to place it here. And the next thing we need to do is we need to find out what is the impedance. Now what is impedance? Impedance is the overall opposition to the flow of current, which is offered by the resistor, the capacitor, as well as the inductor when they are connected in series within an AC circuit. And the formula for impedance is Z equal to R squared plus X sub L. This is the inductive reactance minus X sub C. This is the formula for impedance. Now we have already been given the value for the resistance, So we're just going to write it there. This is going to be 70. So this is going to be squared. Now x sub L has been found as a 502.865. Well, so that is going to be subtracted. Well, we need to subtract 7.96. That is the capacitive reactance away from there. So this is going to be 7.96 all squared. So this is 70 squared plus, so this is going to give us so this gives us 499.62. The impedance Z, that is 499.62 ohms. Now the next thing is we need to find the RMS current within this circuit. Now what is going to be the RMS current? We know that V, the voltage from the Ohm's law, is always going to be equal to current multiplied by the resistance. Now we need to find the current. But in this case, we got it as the RMS voltage. So this is going to be VRMS, and that will be equal to IRMS. That will be multiplied by R. So we need to make these as a subject. So in this case, we're going to have IRMS is going to be equal to VRMS, and that will be divided by R. Now what is VRMS? Now VRMS is given as a 200. R was found to be. Now in this case, we're not going to use R. We need to use the impedance. So you just need to remember this. The RMS voltage, that is going to be RMS current multiplied by the impedance. This is for a total series circuit which has the resistor, the capacitor, as well as the inductor connected within it. So that is an RLC series AC circuit. So just hold these at the back. So this must be divided by Z, not R. So that is 499.62. That gives us 0.4. So we got 0.4 amps. This is the current. Now we need to find what is the phase difference voltage between the instantaneous values of the current as well as the applied. Now what is the phase difference? Phase difference is the same thing as a phase angle. Now how can we find it? In order to find the phase angle, you need to take the tan of it. So this is going to be the tan of the phase angle. And this is equal to x sub L minus x sub C. That will be divided by R. So you need to hold this at the back. This is very useful. Now this stuff, what is it? That stands for the normal resistance which was given. That is 70 ohms. Therefore, we're going to have a tan phi be equal to this stuff. Now, what is this stuff? We know that x sub L is this, and x sub C is this. So let us find the difference between the two of them. So that is going to be 502.65 minus 7.96. That gives us 494.69. So this is going to be 494.69. This will be divided by R. Now R in this case is a 70. So tan phi is going to be equal to this stuff divided by 70. And that gives us 7.067. I need to try that again. So that is a 494 minus, well, 0.69 rather. Now will be divided by 70. So that gives us 7.067. Now we need to find this. In order to find this, we need to take the tan inverse of this stuff, which is arctan. So I'm going to clear these out. So phi, which exactly is the phase angle itself, is going to be tan inverse, which is a tan inverse of 7.067. So that gives us 81.95 degrees. So phi, the phase angle is going to be equal to 81.95. So this is what you got. This is going to be the phase angle. Now finally, we need to find the power factor. How can you find the power factor? What is going to be the formula for it? So I'm going to take this one out. Now the formula for the power factor is given as a cos phi. That is going to be equal to R divided by the impedance. So in order to get that cos phi, that will be equal to R. Now R is a 70. This will be divided by Z. Now Z, that is the impedance, which was gotten to be 499.62. So let us see what that is going to give. So that gives us 0.14. So 0.14 is going to be the power factor. So you need to hold these at the back. These are going to be the answers for this question. Now here is the next question. The voltage of an AC source is given by the formula Vt is equal to 220 root 2 sine 100 pi t. Now what is going to be the RMS voltage from here? Now we know that instantaneous voltage V is always given as V0 sine omega t. So from here we got V, that is equal to 220 root 2 sine omega t. So from here we can see that V0, that is equal to 220 root 2. So in order to find out what is going to be the RMS voltage, that will be equal to V0 divided by square root of 2. Now this stuff is given here already. So that will be 220 root 2 divided by root 2. Now this is going to take these out. So this should give us a 220 volts. So in that case, we're going to have this. This will be the answer. Now from here, how can you find what is omega? We have that. So I think I needed to write this out. This was a 100 pi t. So as you can see, we got sine omega t, and that is equal to sine 100 pi t. So as we take these ones out, we're going to be left with omega t, and that will be equal to 100 pi t. This stuff is also going to cancel. So we're going to be left with omega, and that is equal to pi. We already know that omega, that is 2 pi f. And on this side, we got 100 pi. So as we take pi out, we're going to be left with 2f equal to 100. And so from here, we can see that the frequency is going to be 50 hertz. Now, let us designate the voltage that passes through an inductor as V sub L. And the voltage that passes through the capacitor, let us call it V sub C. And let us see that the voltage that passes through the resistor, that will be represented as a V sub R. Now, generally, you're going to have the voltage that passes through the inductor represented on top this way, and the voltage that passes through the resistor, that will be written this way, and you're going to have the voltage that passes through the capacitor written this way. Now, if you want to find out what is going to be the difference between this voltage and this voltage, that is obviously going to be V sub L minus a VC in it. So I'm just going to draw that here. Let us see, that is this stuff represented here. I think I need to redraw that. So this is what you got. Now as we go this side, we're going to have a VL minus a VC. Now if you got VL minus a VC, which is a potential difference across the inductor minus the potential difference across the capacitor, if you got this stuff being greater than 0, then you need to know that the current in this circuit is going to lead the voltage that will be produced or released. So that is it. But if you have a VL minus a VC being less than 0, then you're going to have that the current that is going to lag the voltage. So always for capacitors, because if you got this to be greater than the voltage that passes through the inductor, you're always going to have a negative value. Now if you got that, that means the current would always lag the voltage. But if you got VL being greater than VC, then the current would always lead the voltage. So you just need to hold that at the back. Now, as far as we got this, I could find out what is going to be the total resistance offered by this circuit. So here I'm going to say this is a Z. So let us find out what that is going to be. This obviously resembles a right angle triangle. So I'm basically going to use the Pythagorean method to find out what is going to be the resistance or the impedance in this case. This is going to be the total resistance, and this stands for the impedance. Now from the Pythagorean theorem, Z squared should be equal to VR squared. Well, so instead of writing this, I needed to make these as a V sub Z rather. So this is going to be a V sub Z. This will be the total voltage as a result of all the elements or the devices which are present within the AC circuit. That is the inductor, the capacitor, as well as the resistor. So that is what we're going to have. Now this plus V sub L minus a V sub C, or raised to the power of a 2. We know that this is going to be the resultant. Now, what is VL? That is a voltage that passes through the resistor. Now that will be current multiplied by the resistance offered by the resistor, which is represented by XL. This is the inductive reactance. Now this is going to be I X sub C. This is the capacitive reactance, and this basically is going to be IR. Now because we got all these devices connected in the AC circuit in series, we're going to have the same current virtually passing through all of them. So I is always going to be the same. Now, what is going to be V sub Z? V sub Z, this is going to be the overall voltage. And the overall voltage is going to be I multiplied by the overall resistance. Let us represent that as a Z. So in this case, we're going to have this. Now we needed to place a square here, because from the Pythagorean theorem, we always got to have the hypotenuse be squared, and stuff which is on these other side must be squared. So in this case, we're going to have a I multiplied by a Z, that will be squared. On this side, we're going to have a I multiplied by R. That also is going to be squared. And here we're going to have a Ix sub L minus a Ix sub C. This is also squared. So we need to factor R out. So I'm just going to take it this side. We have a I squared Z squared. And on this side, we're going to have an I squared. This is going to be R squared. This will be plus, basically, I squared XL minus XC all squared. Now from here, we can factor I squared out. So I'm going to take these out for now. I think I'm going to take all these out also. So this is going to be I squared Z squared. And that is going to be equal to I squared multiplied by R squared plus X sub L minus X sub C. This is going to be squared also. So from here, we can cancel these things. So this is going to be Z squared. Z squared is going to be equal to R squared plus a X sub L minus a X sub C. Now from here, we can find out what this is. This stands for the impedance of an RLC circuit, which is actually connecting the resistor, the inductor, as well as the capacitor in series. So that will be the square root of everything there. So that will be R squared plus this. So this is what you're going to have. This stands for the impedance of a circuit. Now, XL stands for the inductive reactance. So in this case, we should have this 2 pi FL. This could also be represented as a omega L. And then we also got X sub C. This is 1 divided by 2 pi FC. And this will be 1 divided by omega C. I could take this and plug them into this stuff. So how is that going to look? So I'm going to take these out. So Z, in this case, that is going to be equal to R squared plus this will be omega C, or omega L rather. This will be minus 1 divided by omega C, and that is squared. And this stuff is going to be raised to the power of 1 over 2. Now you just need to know that this is the same thing as the square root of that. So there is actually no difference from it all. But you just need to know that this is the same thing as this other one. Now what is the phase angle? Like we solved it initially, the phase angle is always going to be this, tan theta. And basically this should be called as a phase difference. That is tan phi. That must be X sub L divided by Z minus X, well, this should be R. This is divided by R, and you got X sub C divided by R. And because we got this, we could take these as a lowest common multiple, and so this should be tan phi. That will be equal to X sub L minus X sub C. This will be all divided by R. So you just need to hold these at the back. The phase angle, this is what it is. Now what is going to be the power factor? The power factor is written as a cos phi. That will be R divided by Z. Now Z, we have Z to be the impedance of the RC circuit. So you just need to basically bear these ones at the back. This is going to be very useful. Now you just have one more question. If you got something like this, so I'm gonna rewrite this. Let us say that X sub C, or rather, let me write as this, XL minus XC is greater than 0. Now if you got this, you're always gonna have a positive value for the phase angle. the phase angle would have a positive value. So I'm going to write it here. Phase angle, that would always be positive. And you know that current is basically going to lead. So current, well, that should be lagging. Current is going to lag the voltage. By what amount? The current would always lag the voltage by 90 degrees. Now 90 degrees is the same thing as a pi divided by 2 radian. And if you got x sub L minus x sub C being less than 0, the phase angle would always be negative. And current, that is now going to lead the voltage by a value of pi divided by 2 radian. Now you need to know that pi divided by 2, that is similar to 90 degrees. So make sure you bear all these nuggets at the back. They're really going to come in handy. A series RLC circuit consists of a resistor of 20 ohms, an inductor of 50 millihenries, and a capacitor of 200 microfarads. So we are asked to find what is going to be the resonant frequency. Now, what is resonant frequency? Resonant frequency always represented as a F sub 0. That is the frequency at which the inductive reactance is going to be equal to the capacitive reactance. Now, inductive reactance, that is a omega C, omega L rather, and that is going to be 1 divided by omega C. Now, because we are asked to find out what is going to be the frequency, we need to express this a little bit further. So this is going to be 2 pi f multiplied by L. And on this side, we're going to have a 1 divided by 2 pi f. And we're going to have a C right there. So we need to find f. Now we're going to take this and multiply it with this other one. So that should give us a 4 pi squared. And this is going to be f squared. So this is f naught. That is equal to 1. Well, so I forgot to complete that and write the LC. So this is equal to 1. And so we need to find this. In order to do that, we need to take these ones away from it. That will basically be as a result of dividing through. So that is going to be divided through by 4 pi squared LC. That is going to give us 4 pi L squared, well, LC rather. So we need to find the square root of this. So if we took the square root of both sides, on this side we're going to have a 1 divided by 4 pi squared LC. And so from here, this stuff is going to cancel the square root. So we're going to be left with f naught, which is the resonant frequency. And we can split this by the method of surds. So this should be root 1, and this is going to be root 4 pi squared LC. Now 4 is a perfect square. Pi squared is also a perfect square. So we could really find out what their square roots are. Now this is also going to be a perfect square. So this is f naught being equal to 1, which is the square root of a 1. And the square root of a 4, that is a 2. Square root of a pi squared, that is a pi. And this will be root LC. This is basically what is going to be left. So this is a formula that you need to find out what will be the resonant frequency within an AC circuit. So what is some L? Now, L in this case was given as a 50 millihenries, which will be rewritten. That will be 50 multiplied by 10 to the negative 3 henries. Capacitance, that is 200 multiplied by 10 to the negative 6. We know that micro is a 10 to the negative 6. So we need to plug all these. So F naught, that is going to be 1. That will be divided by 2 pi multiplied by the square root of this stuff. So this is going to be L, which is a 50 multiplied by 10 to the negative 3. And this will be multiplied by 200 multiplied by 10 to the negative 6. So let us see what that is going to give. So that is so that gives us 50.33. So we got 50.33, which is basically or approximately same thing as a 50.3. So that is going to be 50.3 hertz. So here option B is going to be the correct answer. Now let us try some questions under electric fields. So the first question says a charge 4 microfarad. So this is actually some wrong stuff. This should have been written as a 4 microcoulomb. So just correct that. Now a charge 4 microcoulomb is placed 60 cm away from the charge minus 4 microcoulomb. So what is the electric field at a point P, midway between the charges, and also at a point Q, which is 40 cm from P and equidistant from the two charges? So let us say that the line that joins them is written this way. Okay, I'm going to redraw that. Okay, so on this side we're going to have I'm just going to write a positive Q here, and here we're going to have a negative Q. Now positive Q, that is going to be 4 microfarad, well, microcoulomb rather. Here is going to be negative 4 microcoulomb. Now the distance between these two charges has been given as a 60 cm. So this is going to be 60 cm. I'm going to write it here. Now they asked us what is going to be the electric field at a point P, midway between the charges. So that is going to be at this position. So midway, this is going to be 30 cm. So this is 30. Well, on this side we're also going to have a 30. So this is what you got. We need to find the electric field. Now we know that force, the electric force, is given as a Q multiplied by the electric field. Now what is electric force? Electric force is basically given as a K Q1 multiplied by Q2. So in this case I'm just going to say Q squared. That is two charges. That is divided by R squared. Now on this side we're going to have a Q multiplied by E. So this is what we got. Now from here we can see that this charge on the right hand side is just basically going to take out one of it on the other side. So in this case we're going to have E, the electric field, that will be equal to KQ divided by R squared. This is a very useful formula, so you just need to really hold it close to you. And we're going to use it to solve this question. Now we're going to have R in this case to be 30 cm. But we know that 30 cm, that is going to be 30 multiplied by 10 to the power of a negative 2 in meters. So in order to find out what will be the field at this position, we need to find out what will be the field as a result of this, and also the field as a result of this. So the field as a result of this, that is going to be E, and that will be equal to K. Now we know that K is 9 multiplied by 10 to the power of a 9. This is multiplied by Q. Now the first one is basically going to be a 4. So we got a 4 here. This is multiplied by 10 to the negative 6. So we got to plot a R squared. So this is going to be 30 multiplied by 10 to the negative 2. And this is all squared. So that gives us 4. 4 multiplied by 10 to the 5th. So the electric field here, that is a 4.0 multiplied by 10 to the power of a 5th Newton per Coulomb. Now, this is what you got. Now, how about this other charge? Is it gonna create a electric field at this point? Of course it is. Now let us find that. That is basically still gonna give us the same thing because we have it to be 4 microfarad, and so that will basically be the same thing. So there is gonna be a total electric field as a result of that. So I'm basically gonna write that as a ET, and that will be equal to E1 plus E2. So that will be equal to 2 multiplied by E. That is because E1 is going to be equal to E2 because we have a 4 microfarads here as well as 4. Now, even though we got a negative there, that is not actually magnitudinal. This only tells the type of charge which is there. This is basically a negative charge, while this is a positive charge. Now, this would only affect the direction of the force. If we got force acting in this position, the force will be directed in that direction, basically. So that is basically what that is going to help us for. Concerning electric fields, these are not consequential. So in that case, we're going to have a 2. We have the value for that to be 4 multiplied by 10 to the power of 5. So this is going to be 2 multiplied by 4 multiplied by 10 to the 5th. So this obviously should give us an 8 in it. So the total electric field will be equal to 8 multiplied by 10 to the power of a 5th Newton per Coulomb. So this will be basically the final answer to that question. Now we need to find out what is going to be the electric field at a point Q. So let us see how we're going to find that. So I need to take these out. I'm going to take these out also. And take these. So here we're told that what is going to be the electric field at a point Q, 40 cm from P and equidistant from the two charges. So if it is equidistant from the two charges, let us say from here to this position, this is where we got Q. I'm going to write this as a Q. And so let us say that this is point P. Point P was given as a point midway, so I'm going to write this as a P. This is the middle point between the first charge and the second. So the distance between P and Q is given as a 40 cm. And this is equidistant between this and this. Between the two charges, so I should have something like this. I think I'm basically going to take these off for now. So this is what we got. Now we know that this is going to be a 30. So this is a 30 cm. And this is also 30 because we know P is the middle point. And here we got a 40. So what is going to be this distance? And because we have that this is equidistant to this, so they're basically going to be the same. But we need to know what is going to be the distance between those two positions. And so in order to find that, we need to extrapolate this. So this is what we have. We got 30 cm over here, and over here we got a 40. So obviously this should have been a 50 cm. Basically, as you calculate it, you're going to find that. You need to use the formula of x squared is going to be equal to 40 squared plus a 30 squared. Now this is going to give you 1600. This is going to give you 900. So as you add the two of them, you should have 2500. The square root of 2500 is a 50. So that is the reason we're going to have a 50 right there. So I'm going to take these out now. So here we got a 50. So this is going to be the distance from this position to this position. Now that is basically going to be the same thing as this. Now there would actually be no force along this direction, because in this case we have a vertical form. There is a horizontal component of this force running in this direction. And there is another one that goes in the opposite direction. So the two electric fields are basically going to cancel out in the horizontal perspective. So they're basically going to go out. Now what is left will be this one. There is no other component that is going in this direction. So there is no canceling. So we just need to find out what is going to be the electric field as a result of this in this direction, and as a result of this in this direction. And so that is basically going to be 2 multiplied by E. That will be the total energy. In this case, we just need to change the distance between the two positions. So this is got to be E is equal to 2 multiplied by KQ divided by R2 squared. Now R2 in this case is going to be a 50. So I'm going to take this part out. So E, that is going to be equal to 2 multiplied by K, which is a 9.0 multiplied by 10 to the 9. And we got a Q there. So we know Q, that is basically the same thing. That will be 4 microfarads, 10 to the minus a 6. And this will basically be divided by R squared. So in this case, we got a 50. That will be 50 multiplied by 10 to the negative 2. And that will be squared. So let us see what this is going to give us. So that is going to be 2 multiplied by 9.0 times 10 raised to the power of a 9. That will be multiplied by 4 multiplied by 10 to the power of a negative 6. Yep. So we are correct on that. Now we need to have a 50 multiplied by 10 to the negative 2 here. And so that gives us a 2.88. So I'm basically going to have that as a 2.88 approximately. That will be 10 to the power of a 5 Newton per Coulomb. This is going to be the answer. The total electric field as a result of these two parts, they are actually going to be equal to 2.88 multiplied by 10 to the power of 5 Newton per Coulomb. Now the second question says, an electron is placed at a certain point in an upward directed electric field of 4 Newton per Coulomb. So what is going to be the magnitude as well as the direction of the force on the electron? And what will be the charge on a small particle of mass given as this? 2 multiplied by 10 to the negative 9 kilogram for it to remain stationary when placed in a field. So first we need to find out what will be the force on the electron. Now electric force could also be represented as a Q, that is a charge, multiplied by the electric field intensity. So we got the electric field intensity as this. In this case, we got the charge to be an electron. So this is basically got to be the charge of an electron. So that will be Q sub E multiplied by E. Now, what is the charge of an electron? That is 1.602 multiplied by 10 to the minus 19 coulombs. And so we got E, that is equal to 4 Newton per Coulomb. So this force is going to be equal to 4 multiplied by 1.602 multiplied by 10 to the negative 19. So that gives us 6.408. That is multiplied by 10 to the minus 19 Coulomb. Or 19 newtons rather. So this is what you have in the first case. Now in the second question, you are required to find out what will make another charge which is placed within such a field. That is a field that carries a 4 Newton per Coulomb. So what will make it to be stationary? In order for that to happen, then you must have the electric field force to be equal to the force as a result of the weight. And the electric field force, that will be written as a QE. And the weight, or the gravitational force, is as a result of the gravitational field, and that is written as this. Now this is the mass of the charge. We were not given the charge, but we need to find out the charge. Now Q is going to be equal to mg divided by E. Now we know that G, that is 9.8 meter per second squared, and so we need to plug all that in. So Q is going to be, we were given the mass as a 2 multiplied by 10 to the power of a negative 9. We got the acceleration due to gravity, that is 9.8. This will be divided by E. E in this case was given to us as a 4. So this gives us 4.9 multiplied by 10 to the negative 9 Coulomb. Now this could also be rewritten as a 4.9 microcoulomb. So you just need to hold these at the back. Question number 3. During fair weather conditions, the atmospheric electric field is 120 Newton per Coulomb. Now, this is directed upwards. So what is going to be the charge on the surface of the Earth, where we have the Earth's radius to be 6,400 kilometers? So first we got the electric field intensity, that is equal to 120 Newton per Coulomb. Now we need to find out what is going to be the charge. So first I'm going to write the R. Now R is going to be 6,400 kilometers. So we need to change this to meters. So this is going to be 6,400 multiplied by 10 to the power of 3 meter. 1 kilometer, that is equal to 1,000 meters. Now I need to change this to standard form. This is going to be 6.4 multiplied by 10 to the power of 3 basically. And so that is multiplied by another 10 to the power of 3. So this should be 6.4 multiplied by 10 to the 6th meters. So this is the real value for the radius. Now we know that F, that is equal to QE in it. Now this stuff we have already said this is equal to KQ squared divided by R squared in it. Now we could take one of the Q's away. So E, that is going to be equal to KQ. That will be divided by R squared. Now what is K? K could also be rewritten as a 1 over 4 pi epsilon naught. So you could also use that. What that means is you could have a Q that will be divided by 4 pi E naught. That will be R squared. So this is another formula for the electric field intensity. So we are required to find out what is going to be the charge on the surface of the Earth. So R stands for the radius of the Earth. So we know that E in this case is going to be equal to Q divided by 4 pi E naught R squared. Now what is E naught? E naught is the permittivity of free space, and that is basically given as a 8.85 multiplied by 10 to the negative 12. So remember this value for the permittivity of our free space. So from here we can see that Q, that will be equal to 4 pi E naught R squared multiplied by E. So that is going to be 4 pi multiplied by 8.85. That will be multiplied by 10 to the negative 12. This is multiplied by R squared. Now R, is a 6.4 multiplied by 10 to the power of a 6. And this has got to be squared. And then we got to square that with 120. And so that will be multiplied by 6.4 multiplied by 10 to the power of a 6 squared. And this has got to be multiplied by 120. So that gives us 54,631.0. That is going to be 0.0899. So approximately what is this going to give? I think I'm going to clear these out and write it here. Q is going to be equal to 5.47 multiplied by 10 to the power of a 5. So this is 10 to the power of a 5 Coulomb. This is going to be the answer. Q is equal to 4.57 multiplied by 10 to the 5th Coulomb. Number 4. Calculate the area of a parallel plate air capacitor having capacitance of 1 microfarad when the plates are separated with 1 millimeter. Now, you need to know that from the Gauss Law, we need to have psi, which is the electric flux, and that is equal to the sum of the charges divided by the permittivity of the medium. Now, in this case, let us say that is free space. Now, psi is also equal to E, the electric field, multiplied by A. So in this case, we're going to see that E, that is equal to Q divided by, well, that should be EA now, isn't it? So that is EA, and that will be equal to Q divided by E now. So I could well find the electric field from here, and that is equal to A multiplied by E now. Now you need to hold this close to you, because this might really come in handy. Now another thing we know is that the potential, electric potential, that is written as a V, and that is given as E multiplied by D. Now if we took this and plugged it into this equation, we're going to have V is equal to Q divided by A multiplied by E naught multiplied by D. So in this case, we can see that V, the potential, that is also equal to QD divided by A E naught. This is also a pretty useful formula. Now let us go ahead and find something more interesting. We know that Q, the charge that is stored in a capacitor, is given as a CV. Now what if I wanted to make C as a subject? C is going to be equal to Q divided by V. Now we already know that V is given as this in it. So here we're going to see that C, that is equal to Q divided by QD divided by A multiplied by E naught. Now this stuff is basically going to shoot up, and so we're going to have a Q multiplied by A multiplied by E naught, and that will be divided by QD. So in this case, we know that this is going to get cancelled. I think I'm going to take that back. Just going to take these out. So from here, we can see that the capacitance, that will be equal to A multiplied by E naught, and that will be divided by D. Now, what is D? That is going to be the distance between the two parallel plates in a capacitor. This is the distance D. Now A, that stands for the area, and E naught, that stands for the permittivity of a free space. So all these formulas are really useful. So you really need to hold them at the back. Gonna be very useful, as useful can be. So what we are asked here is to find out what is going to be the area. Now what parameters were given to us. So I need to wipe these out. So first we were given the capacitance, and that was given as a 1 microfarad, and that is basically 10 to the negative 6 farads. Now they are separated, so this is the distance, that is a 1.0 millimeter, and that is equal to 10 to the negative 3 meters. So from here we can do it. We could use this formula to find out what is going to be the area. Now E naught, this is permittivity of a free space, that is 8.85 multiplied by 10 to the negative 2. So I'm going to take this one out now. I'm going to take this one out also. So here we can see that A, the area is going to be equal to CD, and that is equal to A E naught. So A, the area, that is going to be CD divided by E naught. Now C, the capacitance, that is 10 to the negative 6. And the distance, or the separation between the parallel plates, that is 10 to the negative 3. And here we got E naught, which is 8 multiplied by, well, 8.85 multiplied by 10 to the power of a negative 12. So the area, A, let us see what that is going to give. So that gives us 112.99. And this is basically going to be 113 meters squared. So that is the area. Now, how can we find the charge? So I'm going to take these ones out for now. We know that C is going to be equal to Q divided by V in it. So the charge, that will be C multiplied by V. Now C, that is 10 to the negative 6. The voltage was given to us as a 5,000 volts. That basically stands for the potential difference. You could also call it as a voltage. So that is going to be 5,000. So let us see. See what that is going to give. So we got 10 to the negative 6 multiplied by 5,000. So that gives us 5. This is 5 multiplied by 10 to the negative 3. So that will be Coulomb. So that will be the answer. Now, what is going to be the electric field created from here? Now, we already know that Q, the charge, was gotten to be 5 multiplied by 10 to the negative 3. We know that the area, we have gotten the area, that is 113 meters squared. And we already know what E naught is. So from here, we could well find out what will be the electric field intensity. So that is going to be equal to Q divided by A E naught. Now Q in this case is gotten to be 5. So that will be 5 multiplied by 10 raised to the power of a negative 3. This is divided by A. Now A in this case is given as a 113 approximately. Now E naught, that is 8.85 multiplied by 10 to the negative 12. So that gives us 5.0 times 10 to the negative 3. And that will be divided by 113 multiplied by 8.85 multiplied by 10 to the power of a negative 12. So that basically gives us 5.0. I'm going to write that as a 5.0. To the power of a 6 Newton per Coulomb. Three capacitors, 3 microfarad, 4 microfarad, and 7 microfarad are connected in parallel to a voltage source of 12 volts. So first we need to find the total charge produced as well as the individual charges on each capacitor. So if they are connected in parallel, then we're going to have a similar or one type of voltage source, which is written as this. And that is going to be this way. And here we're going to have this. And here we're going to have this. So this is basically a parallel connection of capacitors, which we're going to have right here. Now here we got 12 volts. On this side we're going to have a 3 microfarads. I think I'm going to write it here. So we got 3 microfarad. On this side we got a 4. So that is 4 microfarad. And here we got a 7 microfarad. So we need to understand that over parallel connection, the voltage which is going to be wasted over each capacitor is always going to be the same. So if you got the voltage wasted over the first capacitor represented as a V1, and the voltage represented as V2, which is the voltage over the second capacitor, and as well the voltage wasted over the 7 microfarad, if that is represented as a V3, all these are going to be the same. They're totally going to be equal to the total voltage or the EMF that is actually represented or supplied for that circuit. And this basically in this case will be equal to 12.0 volts. So you need to remember this. We're going to use it as we solve. And before we come to the total charge, we need to find the individual charges. Now the charges which will be generated on each capacitor would actually be different. So in that case, we're going to have a Q1, and that will be equal to C1 multiplied by V. We know that the general formula for the charge on a capacitor is represented as a capacitance multiplied by the voltage or the potential difference. So that is represented that way. So the first charge is going to be C1 multiplied by V. Now Q2, that will be the second voltage, second charge rather, and that will be C2 multiplied by V. Q3 is going to be equal to C3 multiplied by V. So we know these voltages are always going to be the same. So you don't really need to worry about that. In the second part of the question, we were asked to find out what is going to be the voltage over each capacitor. And so that really now comes off easy in it. We know that the voltages which will be wasted over each capacitor, they're always going to be the same. So V1, V2, V3, they're the same thing, and that is going to be equal to the EMF source, 12 volts. So what is the first charge? C1 is given as a 3 microfarad. So we gotta have Q1 is equal to 3 multiplied by 10 to the power of a negative 6, and this will be multiplied by 12. So the answer here, I'm just going to write it on this other side. So that is 3 multiplied by 10 to the power of a negative 6, and that is multiplied by 12. And so that gives us 3.6 times 10 to the negative 5. Coulombs. Now let us find out what is going to be the second charge. So Q2, that is going to be equal to C2 multiplied by V. And so that is going to be C2. In this case, C2, that is 4. So that will be 4 multiplied by 10 to the negative 6. That will be multiplied by 12. So that gives us 4.8. So this will be 4.8 multiplied by 10 to the negative 5 coulombs. Now let us go to the third one. So that is going to be the third capacitance multiplied by 12, which is 7. So that will be 7 multiplied by 10 to the negative 6. And this will be multiplied by 12. So that gives us 8.4. So that is going to be 8.4 multiplied by 10 to the negative 5 Coulomb. So that is what you got. Now, how can we find the total charge? So the total charge, that will be Q sub T. That is going to be equal to Q1 plus Q2 plus a Q3. So this is going to be 3.6 added to 4.8, and that will be added to 8.4. Basically, all that should be multiplied with 10 to the negative 5. So this is going to be 3.6 plus a 4.8. Well, it should be added rather. And this is going to be an 8.4 multiplied by 10 to the negative 5. So that is 3.6 plus a 4.8 plus a 8.4. So that is 16.8 multiplied by 10 to the negative 5. So this is going to be 1.68 multiplied by 10 to the negative 4 Coulomb. This is going to be the total charge. Now here we need to find out what is going to be the work done. Now we know that work done, W, that is going to be 1 over 2 QV. This could also be represented, because we know Q is the same thing as CV, so this could also be represented as a CV multiplied by V. So that should give us a CV squared in it. So that will be a CV squared. Now from here, you can see that C is the same thing as a Q divided by V. So we could do that for this one. And so that will be 1 over 2 Q divided by V multiplied by V squared. Well, need to write this better now. Now this could cancel one of the squares, or one of the V's rather. And so that will give us work done, which will be equal to 1 over 2 Q divided. Well, that will be QV in it. So basically what I want to do, I want to change V. So I'm going to replace V with C. So V, that is equal to Q divided by C. Here we have a V squared. And here we have a V. So I think I'm just going to plug that here. So that is going to be work. That will be equal to 1 over 2 Q multiplied by V, which is Q divided by C. So work done could also be represented as a Q squared divided by C. These are the three forms that you could use to find out what will be the work done or the energy stored within a capacitor. So always remember these ones. So based on the parameters which are given to us, we're going to use them. Now this happens to be the simplest, so basically that is the one I'm going to use. So this is 1 over 2 multiplied by Q. Now Q, that is the total charge, which is given as a 1.68 right now, and that will be 10 to the negative 4 multiplied by the voltage, which is given as a 12. And so we need to find what that is going to be. That is 0.5 multiplied by 1.68. That will be multiplied by 10 to the negative 4. This will be multiplied by 12. So this gives us 1.0 times 10 to the negative 3 joules. Number 6. What is the charge produced on a spherical metal ball of radius 2.35 millimeter when charged to a voltage of 30 volts? So the radius that we got here, that is 2.35. Now we got the voltage V to be equal to 30 volts. So how can we solve this? Now the capacitance of a spherical capacitor, that is equal to 4 pi E naught R. This stuff is what we gotta use. Now if we find this, we can find a charge, because charge is going to be equal to CV. Now, from here we could well see that charge is going to be equal to CV, that is 4 pi E naught R, and that will be multiplied by V. So we could well straight ahead just solve it in this way. So this is 4 pi E naught, which we already know that is a 8.85 multiplied by 10 to the negative 12. And this will be multiplied by R. Now R is a radius, so that will be 2.35. This is going to be multiplied by the voltage. Voltage is 30. So Q, that is going to be 4 pi multiplied by 8.85 multiplied by 10 to the power of a negative 12. And this will be multiplied by 2.35. That will be multiplied by 30. So that is 7.84 multiplied by 10 to the negative 9. So this is going to be the answer. Now, from this other way, you could also find out why that is. We know that potential is a work done on a charge. Now, work done is the same thing as a force divided by distance. This will be divided by Q. Well, this is force multiplied by distance rather. Now, force, we got that to be KQ squared divided by R squared. This is multiplied by D. In this case, I'm just going to make up this D, which is distance, as R. This is pretty much the same thing. So this will be divided by Q. From here, we can see that R is going to cancel one of it. And so we should have a K Q squared. And that will be divided by QR. And so Q is also going to cancel one of it out. So we're going to have a V. V is equal to K Q divided by R. Now, since we already know that K is equal to 1 over 4 pi E naught, we're going to take that in. So V, that is going to be equal to 1 divided by 4 pi E naught. That will be multiplied by Q. This is divided by R. This stuff is going to sink down. And so we're going to have V. V will be equal to Q. I'm going to write it with an uppercase. So that will be divided by 4 pi E naught R. So this is a formula for that. If you plug in your values here, you're going to get this same answer. So that is basically the same thing. From here, we can see it clearly. In order to get Q, you need to multiply this with this, which is still going to give us this. Q will be equal to 4 pi E naught and R multiplied by V. And that is the same formula as what we got here. Number 7. In the hydrogen atom, the electron orbits the proton under the influence of an electric force. So if the orbit radius is 5.29 multiplied by 10 to the negative 11, what is going to be the potential energy of the electron in its orbit? Now we know that W. Instead of doing this, I'm going to write it this way. V is equal to W divided by Q. And so we're going to see that W, which is a potential energy or work done, that will be QV. Now what is V? We already know that V is equal to KQ divided by R. This stuff is going to be Q in the uppercase. Now this stands for the charge of the electron, while this stands for the charge of a proton, which is basically the same thing. So the charge of an electron, that is equal to the charge of a proton. So I'm going to write that as Q sub P, and that is 1.602 multiplied by 10 to the minus 19 coulombs. So as I take this to plug it here, we're going to have a W, and that is going to be equal to Q multiplied by K, Q divided by R. Now we already know that K, that is equal to 1 multiplied by 10 to the power of a 9. So here we're going to have a first Q. Let us say this is the charge of a proton, this is a charge of an electron, which are basically going to be the same thing. So this is still going to be 1.602 multiplied by 10 to the power of negative 19. This will be multiplied by K, which is 9.0 multiplied by 10 to the power of 9. Now multiplied by Q sub E, which is basically the same thing. Minus 19, and this is going to be divided by R. R is the radius. Now the radius, that is 5.29 multiplied by 10 to the power of negative 11. So that is going to be 1.602 multiplied by 10 to the power of negative 19. This stuff is going to be squared. So that is going to be squared. And so we're going to have this. This is going to be multiplied by 9.0 multiplied by 10 to the power of 9. And this will be divided by 5.29 multiplied by 10 to the power of negative 11. So this gives us 4.37 multiplied by 10 to the negative 13. This is going to be the answer. Number 8. Point charges 8 microcoulomb minus 15 microcoulomb and plus 12 microcoulomb are placed respectively at points A, B, and C at the corners of an isosceles triangle. And the distance between A and C, 24 cm, is the base of the triangle. And AB is equal to BC, which is equal to 13 cm. Now there is actually a conventional diagram which was already given. Should have given that, but actually forgot that, so I'm just gonna draw it here now. So this is what you got. So there must be a midpoint. This is the midpoint. So the base, which is A and C, so this is going to be A, this is going to be C, and this point is a D. Now from here, from this point until you reach this point, this is actually the base of the triangle. Now that was given to be 24 cm. Now point D is the middle. So from here to this place, that should be 12 centimeter. Here is also going to be 12 centimeter. Now we know that at point A, there is 8 microcoulomb in it. So this is going to be 8 microcoulomb. Now at point C, that is a positive 12 microcoulomb. Now at point B, so this is going to be point B. At that point, we're going to have a negative 15 microcoulomb. Now they were given the distance between A and B, as well as B and C. They are basically equal, so this is going to be 13 cm. So from here, we need to compute the potential, as well as the potential energy at the point D. So at this point, we need to find it. So you need to know that we need to resolve this. First, we need to find the potential at this point as a result of this, as a result of this, and as a result of this, and add them basically together. So what is potential? V is basically W divided by Q, which is the same thing as KQ divided by R. Now R is basically going to stand for the distance. So first, we're going to find the first one. So that will be VA. I'm going to call it VA. So that will be equal to KQ sub A. That will be divided by R sub A. This stands for the charge at A, and this stands for the distance of the charge A from the point D. So Q, that is 9.0 multiplied by 10 to the negative 9. This is going to be multiplied by Q sub A. So that is 8 microfarads, that is 10 to the negative 6. So here we're going to have a R. Now, the distance between that is 12. So this is going to be 12 multiplied by 10 to the negative 2. So that gives us 6.0 times 10 to the 5th. I'm going to write that here. V sub A. That is going to give us a plus 6.0 multiplied by 10 to the 5th volts. Now let us go right ahead and find what is going to be VB. So VB, that is a voltage felt at this position as a result of the charge placed at point B. That typically should be KQ at B. That will be divided by R placed at B. So this again will be 9.0 multiplied by 10 to the power of 9. This will be multiplied by Q at B, which is going to be a minus 15 multiplied by 10 to the negative 6. This is going to be divided by R at B. So we need to find this distance. We have not found it. Now if you got this triangle, and this part is a 12, and this is a 13 rather, and this is a 12. You need to know that this is a 5, 12, 13 right angle triangle. If you go by the Pythagorean equation, you're going to find that this part will be 5. So just go ahead and try to do it. So this is 5 cm. So this is going to be 5 multiplied by 10 to the negative 2. So let us find out what that is going to give. So that gives us as VB now. VB is equal to minus 2.7. Well, I'm just going to write it as a 27. Multiply by 10 to the 5th volts. So finally, we're going to find out what will be the voltage as a result of the third charge. That is plus 12 microfarads. So that is going to be V sub C. That will be Q sub C divided by R sub C. Now K rather, that is 9 times 10 to the power of 9 multiplied by plus 12. That is already positive, so I'm just going to leave it that way. 10 to the negative 6. This will be divided by RC. Now R, the distance between this and this, that is a 12. So that will be 12 multiplied by 10 to the power of a negative 2. So what is that going to give us? That will be divided by 12 multiplied by 10 to the power of negative 2. So that gives us 9.0. V sub C, that is a positive 9.0 multiplied by 10 to the 5th volts. Now in order to find out what is going to be the effective voltage, so that is going to be written this way. That will be equal to VA plus a VB plus a VC. So this should be equal to plus 6.0 multiplied by 10 to the power of 5. And that will be multiplied, they should be added rather. I'm a little bit used to that, to multiplying things now. So I think we'll need to hold these ones this way. I'm going to use green. Do that. So that will be minus. And here we got to place. So this is 10 10 raised to the power of 5. This is plus, so this is going to be plus. I'm basically going to place this one here. So we got a 9.0 multiplied by 10 to the 5th. So basically that should be 6 minus 27 plus a 9.0. That gives us a minus 12. So the total or the resultant voltage, that is going to be 12, or a minus 12 rather. This is a minus 12 multiplied by 10 to the power of a 5 volts. This will be the answer. Now we need to find out what is going to be the potential energy. How can you find that? So we know that potential energy, V, well, this is W rather. Before we do that, we know that from this position, V is equal to W divided by Q. So in order to get that, we need to find this. So this is going to be equal to W, which will be equal to QV. Now we know that V, this is what it is. Now what is going to be Q? How can we find it? Now in order to do that, we need to find the work done as a result of this, the work done as a result of this, and as a result of this. However, we need to use one thing. Instead of using that, we were given some. So this question is a lot not written completely as it was required. You were asked that if you got a charge Q, which is equal to 20 multiplied by 10 to the negative 6 Coulomb placed at the point D, what is going to be the potential energy? So this is actually what we should have used. So this is what we're going to use. So W, that is going to be equal to 20 multiplied by 10 to the negative 6. That will be multiplied by V, which is equal to 12, negative 12, multiplied by 10 to the power of 5. So I really need to place this minus here. So first I know that this is going to help us have a minus 24. So this is going to be minus 24 basically, minus 24 joules. Now here is the ninth question. A charge, 3 nanocoulombs, is placed in an electric field of magnitude 8 multiplied by 10 to the 5th Newton per coulomb, upwardly directed. Now what work is done by the electric force in moving the charge 60 cm to the left, 50 cm downward, and 180 cm upward at an angle of 30 degrees to the vertical? Now we know that work done, or the voltage, is going to be work done divided by Q. So work done should be equal to QV in it. Now we were not really given this, so we cannot really use this formula to find out what is going to be the answer. So we're not going to go with this. We also know that work done is basically going to be F multiplied by S. Now what if the rod or the charge or the motion of the charge is inclined at some angle theta with the electric field? Now if you got that, that is going to be F cosine theta, which is going to be the horizontal component, and that will be multiplied by S. So this should be F multiplied by S cosine theta. S is going to be the same thing as the distance. So W is equal to F multiplied by D. That is multiplied by cosine theta. Now what is F? F is the same thing as Q multiplied by E. So W in this case is going to be the same thing as a QED cosine theta. Now it happens to be that we have all the parameters here. So let us go on to the first case. If we got 60 cm to the left, That means work is going to be equal to Q, which is that is 3 nanocoulomb. So that will be 3 multiplied by 10 to the negative 9. Nano is equal to 10 to the negative 9. Now, if you got micro, that must be 10 to the negative 6. If you got nano, that will be 10 to the negative 9. And if you got pico, that will be 10 to the negative 12. Femto, that will be 10 to the negative 15. How about 10 to the negative 3? That should be a milli. So that is 10 to the negative 3. So just hold these at the back. They're really going to be handy as you come to solve questions. So Q is 3 multiplied by 10 to the negative 9. Now the electric field was given as 8 multiplied by 10 to the negative, well, that is to the power of 5 rather. Now we got the distance, which is given as 60. And so this is going to be 60 multiplied by 10 to the power of a negative 2. Now, the magnitude of the electric field into which this charge was inserted was 8 multiplied by 10 to the 5th. Now the direction is upwards. Now, if you got the charge moving in this direction to the left, what is going to be the angle? That is the angle between the electric field and the motion of the charge. Obviously from here, this is going to be theta is equal to 90 degrees. So in that case, we need to have a cos 90 degree written there. So I need to write that. Now we already know that cosine 90 is basically going to give us 0. So the work done here should be 0 joules. Now in a second case, we're going to have a QED cosine 50 cm downwards. So we got the electric field in its direction, and the direction of the charge is in its direction. So in this case, we're going to say this is 180 degrees. So that will be QED cosine 180. So this is going to be 3 multiplied by 10 to the power of a negative 9. And that will be multiplied by E, which is 10, well, 8 multiplied by 5. Multiplied by 10 rather, raised to the power of a 5. And multiplied by the distance. The distance in this case is a 50. So that is 50, 10 to the minus 2. Because we got 50 cm here. And that will be multiplied by cosine 90. Well, so this should be cosine 180 in it. So this is 180 degrees. That is multiplied by 8 multiplied by 10 to the power of a 5. And that is multiplied by 50 multiplied by 10 to the power of a negative 2. This will be multiplied by cosine 180. So the answer here is a negative 1.2 multiplied by 10 to the negative 3. You could also write this as a negative 1.2 millijoules. This is milli. Do you remember that? Now finally, we need to find the work done in a case where we got 6 or 30 degrees rather to the vertical. That is 180 cm. So I'm going to take this a little bit upper. So this should be 3 multiplied by 10 to the negative 9 multiplied by 8 multiplied by 10 to the 5th. And this is multiplied by 180 by 10 to the negative 2. We know this should be cosine 30. So what is that going to give? So we need to change that. That should be 180. So that gives us 3.74 multiplied by 10 to the negative 3. So from here we could say this is a 3.74 millijoules. So those are going to be the answers to this question.